Ladies and gentlemen, please welcome to the stage Gareth Rogers.
I'm Gareth, I'm from Cambridge in the UK, and I work at Metail. I'm going to be talking about the functional paradigms we've used to build our data analytics pipeline. So thank you for coming to my talk. I've got to remind myself it's exciting and not scary to be standing in front of a cinema screen. It's certainly the largest I've ever seen my slides projected. And so I'm going to be talking today about Metail's data pipeline. And to do that, I'm going to actually explain who Metail are and what we do, and our pipeline and sort of why we're collecting the data we're collecting. And then I'm going to have a little bit of a sort of more detailed explanation into Apache Spark itself and how we're using that within our pipeline to do some data transformation and can touch on some of our experiences. So first thing, who are Metail? Well, we have a mission, and that mission is to make clothing fit for all. And we've got two primary products that we're doing this. And the first one we've got, coming sort of chronologically, this is the idea that our CEO founded Metail on, is the Metail experience. And so this, you have to sort of imagine yourself shopping online. You come into a retailer's webpage, and you're seeing a lot of clothes that you want to buy. They're being worn by models. But you can't really get from that how those clothes are going to look like on you. There's a vast range of body shapes that people can take, and a model image will take only a single one. And so what we set out to create was a way to try clothes online, and with a minimal input of just your height, your weight, your chest size, we can create a 3D model of you. And using our own digitization pipeline, we've separately digitized the clothes. And so we can simulate those clothing on your 3D model, which then allows you to sort of have some interactions on the retailer website and see how that item of clothing might look on you, and also to build up outfits to get a better feel for how that might look with something you already own or something you're trying to buy perhaps for an evening out. Now, from my perspective as a data engineer, I'm more sort of interested in the actual events they're sending slightly more than the use case of it. And so for me, this is sort of a clickstream analysis product. It exists with something we sell to the retailers and not directly to consumers. So our only interface with the customers who are using this via a retailer website is the actions that they perform within the app and the events then we collect about what they're doing. And so if we want to understand how the user journey is working in our product, what features people are using, what they're ignoring, what's working well, what's not, that comes from this clickstream analysis. We have to collect this data, transform it, and make it available for people to look at. And additionally, as we're selling to retailers, they want to know that we're not impacting their performance. And so we need to know that we're not impacting their performance as well. And so we also want to be looking at key performance metrics, things like conversion and the revenue per visitor. And all of that needs to be kind of come through the system and be able to be visualized and understood by our marketing department, business development department. We have data scientists as well that are investigating and modeling this data. Our second product is again a second one related to fashion. And this sort of imagery you see on the retailer's website. And so we realized that retailers have so much of a problem, but it's quite expensive for them to get this model imagery up on their websites. So you see someone wearing a dress, a shirt, that was a photograph of that was a model, took the time to put that on, to pose in various items. There's a lot of photography and makeup all goes on with that. We realized that we could just singly take a picture of the model in their underwear, and then using our garment digitization pipeline, now we can combine those two, the model image and the garment image sort of offline digitally to produce a rendered image of the model wearing those clothing. And so this helps to reduce the cost for the retailers. Now they only need to do the model photography once, probably in a few poses, And then every new garment that comes through, we photograph, and we can do that at a much higher rate than if someone has to be trying on those clothes. But that image is something we just sell to a retailer, and then they use pretty much as they wish. We have no understanding of how that's being used on their websites. So for us, this kind of analytics is more about the tooling we're using in our digitization pipeline. So we've written tools to digitize these images, and we're giving these to people who we can interact with well, and we're training to do this imagery. So we need to now understand how they're using it. Are they using it as we've asked them to? Where are the bottlenecks in the pipeline? What optimizations we can try? And then if we try some optimizations, do they work? And yeah, just generally understanding the costs of our digitization, so we can sell these things at a profit to retailers. And so yeah, it's quite a different sort of set of analytics events, and it's actually a much smaller scale. But all of these we can put through our same pipeline, and you're using very similar principles to process. And yeah, what are those principles? Our pipelines are all very much influenced by functional programming paradigms. It was we had some functional programming languages already in the company doing other things before we started building out this pipeline, possibly 5 years ago. And so we sort of reading around, we've seen that people are using these kind of things. And so a lot of our pipeline is utilizing immutable data structures. So that's the case where rather than going around and having one copy of a data and editing it, we're now making copies with transforms. And there are ways to make that more efficient depending on the context. But yeah, the rule is you don't go back and fix a mistake, just make a new copy with that mistake fixed. A lot of the tools we're using are very declarative, and this can be very helpful for us as a small team because we're sort of describing what we want to do, and it's something else's responsibility to produce a much more optimized plan of how to do that. A simple common example would be SQL, where you write your select statement and then something very magical happens in the background when you send it to the server. And yeah, finally, this sort of use of pure functions and minimizing side effects. This makes it much easier for us to reason about the system and to test the system. Some of the times we're dealing with cases where the data is being processed in a distributed environment, and so things might fail and be retried, and you can never. It's quite easy to perform things more than once. And so by using pure functions, where you take the data that you wish to process, and that's the only thing you're dependent on, you transform that and you return your answer, you know that that's very robust to being called more than once. It's actually quite cacheable as well if we know that some response has been the same. And so maybe a simpler example of this is if you want to increment a number in a row, some column, some cell, you want to increment that number rather than taking a reference to a row in a database and then having the function make that change. Instead, we give it the row itself. The function increment returns a new version of the row with that column incremented. And this means it can be executed multiple times speculatively in distributed environments without having to worry about managing that sort of concurrency with the database. Of course, we'll need to write those rows later to a database, but we can do that in a much more controlled environment where we know we're in a sort of more single-threaded. That's the idea then of minimizing these side effects. Is where we have to do something complicated, we try and do it in a much more controlled environment. And so by doing this, it does allow our code to be more unit testable, because you have to sort of mock up much less infrastructure in order to test it. And so there are sort of examples of pipelines that are out there that we found when we came to build this that are sort of very much utilizing these principles. And one of them is the Lambda pipeline, Lambda architecture, sorry. And itself is must be 5 more years old now. It really came out, sort of got solidified in the era where Hadoop was very much at its peak. Disk was cheap, but CPU was still a little bit of a scarce resource. And so people had moved from a single SQL databases up into the distributed environment of Hadoop and needed to kind of store very large data sets in a distributed way, but still have responsive dashboards. And So the idea was that you have your immutable data set, and this is a raw data that will come into the system and is put out into a distributed file system. And then, very much like you might do in a standard database environment, you create views upon this database where you're sort of gradually condensing down your raw data into something smaller and more aggregated, much cleaner, generally much higher processing, which makes it easier for people to query against. But additionally, what this brings you is now a concept of you're only dealing with the new rows that come into the system. So every day or every run, which might be once every few hours, maybe it's some fixed file size, you just take the new batch of data and process only that. And this significantly reduces the amount of CPU you need and the time taken to process a new batch. And then, so again, you're appending to your views in these sort of immutable data sets. And it's something where if you use a sort of intelligent user file format, something schemaed, perhaps like a Parquet format, where you want to add a new column to a data set, this can be done quite efficiently because the Parquet format can handle schema changes by so if you don't need to go back and process the old data, because it will just sort of put nulls in or some default value. And again, you just keep on adding, and you can extend your schema, and the tools will do this for you without having to spend a lot of computer processing the whole thing. Although, of course, if you do need to correct a mistake or want to put a column back on your old data, you would then go back and reprocess the whole thing. And that's a case where you'll create a whole new data set rather than replacing the old. And this can be useful. You might keep a version 1 of some view because you want to go back and be able to refer to that, or perhaps it is completely useless and you would just delete it once you're confident that your new data can replace the old. Okay. So with these batch views, these are sort of things where you're essentially caching your queries to make it much faster for users who want to start from that layer in the data set. But you also have a serving layer, which is probably some kind of data warehouse SQL engine, which you can connect business intelligence tools to and produce dashboards to now allow people to sort of visualize the system and see the metrics that the system's producing. The Lambda architecture also has this speed layer inside it, where at the time, so this was a case where there wasn't really enough compute available to process all the data. And so the idea was you just downsample, maybe take 1 in 1,000, 1 in 10,000, depending on the size of your events, and you could process that in real time and be able to spot errors in the events. Since this was formalized, the world has moved on. Streaming processing is common now, and I think the Kappa architecture largely, sort of to some extent, superseded this. But we're still in the batch world and we never implemented any real-time monitoring because we're able to do it fine with the batch frequencies we had or have. Okay, so it's sort of a bit of a almost theory about our pipeline and some of the paradigms we're using to build it. I'm going to talk now just a bit about how we're actually driving the pipeline. And this is something where we ended up writing our own custom tool in a language called Clojure. It was a functional programming language that we have experience with in Metail. And we thought it would be a good fit for writing this driver pipeline. Because it's Clojure, just to talk a bit about Clojure itself for those who don't know, it aims to be an approachable language, which I personally found to be the case. I don't know if that's just because I like to think in a data-driven way, but coming to it from Python, I found the different paradigms of Clojure still very, very easy to get into. It does very usefully, I think, particularly for developing pipelines and transforming data, allows interactive development. So this is where, just much like in Python, you can start an interpreter, type in some code in Clojure, you can start your REPL, you can start writing Clojure and seeing the result. Or perhaps more interestingly, when you've developed a function, you can produce some mock data, put it into that, and just see how it responds, and kind of get a much better feel for how you're developing it, and then hopefully convert those things into unit tests. It's a Lisp, I will show you a bit of Clojure later. The main thing you'll probably notice as a Lisp versus something like Python is the parentheses go around the entire function body. So rather than function name parentheses arguments, you've got parentheses function name then arguments. And in Clojure everything is a list, and as a result the language has a lot of sort of essentially data is code, and so it's a very good choice for building pipelines where you want to be data driven. You want to be able to just describe the thing you want to happen and then use sort of list processing to do it. Clojure is dynamically typed as well, which can help with approachability. You kind of think a little bit less at runtime, but at the same time this does have a drawback when you want to really sort of feel confident that now if you're writing some big job graph that you haven't made a copy and paste error or a typo, like there some kind of type definition might help you out. And there is support within the language for sort of applying schema requirements to inputs and outputs of your functions. And it's something we sort of selectively take use of depending on the circumstance and where we feel will give us some benefit, particularly in the unit testing environments where you can detect errors before deploying them to runtime, deploying them to production. Finally, Clojure itself runs on JVM and on JavaScript, and I've only used it myself on the JVM, and that's kind of sits better in the big data world. We do have people in the company who are writing Clojure script for our web app, and actually the MeTel experience itself you saw is a Clojure script project. Okay, yes. So, sort of, why we're using Clojure? Well, some of the other reasons here is that this is running on the JVM, and given it's got very powerful Java interop, it gave us access to the whole Java ecosystem and the deployment sort of environment around that using Maven, and running JVMs on servers is kind of almost a solved problem. So we're able to, and there's a lot of libraries out there, so we're really able to utilize that. And Clojure also has the advantage of not being Java, so it is much nicer to write and more fun too. So here's a little example of some Clojure over here. I don't really expect anyone to fully follow this. I'm just going to put it in as a little bit of an example of here you've got your first argument, which is actually a function. The function itself is defining a function called this, and this is a job step, a Spark job step using the Snowplow Flix pipeline. And so just being able to use this is essentially equivalent to some kind of like a JSON map. It's a Clojure map, and so we've got our keys, we've got the things we want to perform. And you can see here, this is a case where I wanted to define a schema so that I know that the thing I've largely handcrafted here is correct. There are at least there are no typos in the keys, and the objects associated with the keys are the correct ones. And then, sorry, so I'm using things like this to build up a job graph. Hold on. Okay, that was quite a big slurp on the microphone there. So using all these steps to build up a job graph, process data at various stages, and then we actually have something here. For example, we might grab one of those steps and do something which actually is a lot more procedural now. You're grabbing that step, getting the properties out of it, and then processing it on, in this case, Elastic MapReduce. So that was a Spark job I showed you. So we're running that. And this is a case now where we've got a sort of graph of jobs. These are all just pretty much data. And now actually we've got some side effects where we're trying to process those and execute them out in the real world and get some results back. And the jobs that we're actually processing then in that previous sort of line there are a variety of jobs. We do some things within pure Clojure itself where actually our pipelines don't require a distributed system, because that, although they're actually quite easy to set up these days, and it is kind of tempting to just say, well, I know how to write Spark jobs, I might as well do everything on it. It does add significant time overhead and complexity in testing, because you're now dependent on these cluster resources. And so where the data size doesn't call for it, where they're actually quite well bounded to being up to a few gigabytes, there's really just a sort of kind of well-constrained order of magnitude that we're dealing with. We just process these things in Clojure directly. Again, we can just deploy them out into their own nodes, and do that. However, when we're looking at data sets that maybe in a single batch are probably much more reasonable. We do process things as low as 2 or 3 gigabytes in a batch, but where we might have to scale much up to much larger things, do reprocessing that could be then in the hundreds of gigabytes range. Being able to use a tool like Spark, which can process small data sets, large data sets with the same code base, is it's very useful. It gives us a lot of flexibility. And finally, we do use SQL a lot. Particularly, we've got a sort of a data warehouse where interacting that with SQL and using the business intelligence tools to give our analysts the much more interaction and power over that is useful and the right way to go. Also, we do try to take a pragmatic approach rather than a got a hammer and everything looks like a nail, but pick the right tool. And so, now this is just a bit of a visualization of the whole pipeline that I quite like to draw and reuse. We've kind of got the sort of MeTel experience thinking over here. This is our things that exist outside in the web, and we're pushing through a Spark analytics pipeline. We've got the process digitization pipeline at the bottom there, which is much smaller data sets and just generally get processed directly and end up in our data warehouse and visualized with the tool. So yes, here's a slide just to prove that we do indeed get analytics out of these things. These are some sort of a presentation friendly set of numbers just to show that we can graph stuff and we can gain insights into the pipeline. Okay, so I'm just going to talk a little bit now about Apache Spark and what it is, before kind of giving an idea of how we're using it. I'll start with a quote from, because I have referred to it a lot without explaining it. And so this is just a quote from their website directly. Spark is a general purpose distributed processing engine. And like I say, I have used it to process a single line, just on a JVM locally on my own machine. I haven't got up to terabytes of data. We don't have any data sets that large, but I have done things in the sort of 700 gigabyte range, which tend to be smaller one-off jobs. And yeah, the same code was able to process. I was able to test on very small and then process these very large things. So Spark itself does come from a functional kind of background. It's written in Scala, another functional programming language for the JVM. That makes Spark very declarative. It uses immutable data sets itself, although that's kind of something that happens in the background largely. And it has a Java API as well. So Clojure has very good Java interop, and although Scala is also a language written in Java, if you're actually trying to use Clojure to interact with the Scala code, they use strange compiled class names and other things you end up having to look up on Stack Overflow. So it's generally a lot better and easier to use the Java API, where you can just sort of read things directly out of their documentation. And yeah, so this is just another image I pinched just to say that Spark has sort of these core API and these core languages where Clojure isn't in here. But Scala and Java are, and Java is the language that we're interacting with ourselves. We actually tend to use the core API at the moment, but there's this much more exciting structured SQL engine, data frame engine that we're trying to move our code base to, and they also have another group of things there that I've not looked at, but perhaps streaming might be on my list. Okay, so just give a quick little diagram here of what it means to have a Spark cluster. I mean, we start with our live or compiled code over here, and really for testing, if you want, this whole thing could just be the JVM that you're running right now. But perhaps more interestingly, this can also be a cluster in an environment, sort of a Hadoop cluster, Mesos or Kubernetes. And so what you do, you're writing your job, but you do that by declaring a Spark session, and you build your graph. And you need to submit that graph to the driver through some URL, and that driver communicates with whatever generic cluster you're using. And then these are sent for execution on the worker nodes. And when you're writing this job graph, what you actually find yourself working against is their RDD API. This is a resiliently distributed data set. And this is a nice example of something declarative where I'm writing operations that occur on what to me I'm just sort of imagining as a single data set, but in reality is a data set distributed across several worker nodes, and then Spark is handling sending my code to that execution. And these RDDs themselves are kept in memory, so that just to make the execution much faster than some of the other MapReduce, so the old Hadoop MapReduce world where everything was just written to and from disk continuously. If you're using this RDD dataset, it's not completely declarative. You do find yourself having to think a little bit about partitioning and where your data is, because when you're doing certain group by operations, you may find yourself needing to move data between clusters. And so that does give you a choice on what you want to do. This is just sort of an example of a job graph that you might want to create, sort of based on our clickstream analysis. Just as the kind of thing that we end up writing against these RDDs, where you start with your raw event, and then perhaps you can just filter those into some bad rows that you write out and look at later, or just pretend don't exist, depending on your time constraints. And then, yeah, you can start doing, you've got a filter here, some kind of mapper which takes each row, identifies a user based on your own information that you've stored about different users. You can do group bys, and then perhaps split again. You start, you're going down, looking at user journey, or you're building KPIs. And each of these Spark will create as an immutable RDD. So each new transformation gives you a new data set that you can operate on. And it's this kind of job graph then you get sent to your cluster. So we write Spark slightly differently, I guess, in the sense we're not using Scala or Python, which is the sort of common and obvious choices. We're using Clojure. And that was partially driven by the fact that we already knew Clojure. And so we had to look around and found that someone had produced a library to handle a lot of this interop. Because in addition to just being able to simply call a Java function from Clojure, you also need to be able to serialize your Clojure functions and send those off into the Scala's Java engine to actually process the code, and also just convert between maybe some Java data structures and Clojure data structures, just to make everything a little bit neater and easier for you to handle in your own code. It looks more natural. And so yes, that's what this sparkling library had done. Just again put some bit of code in here just to sort of show that you can write some Clojure and it does work. Got a few fake events of some user IDs, and then which this creates an RDD. You can well imagine this is a file on your cluster somewhere of some JSON, and then first job is to just parse that JSON into Clojure data structure, so I can filter out my corrupt events like this little guy here who's got 7 rather than some kind of string. And then finally we can select group by all get the user ID and then count how many sessions there were per user, or actually events per user, sorry. However, this has limited use because this here is actually a Clojure map, and it's brought the whole results back into memory, into the Spark driver. And actually all these operations are lazy. So as you write down and declare these transforms, Spark doesn't actually immediately execute them. Instead, it builds this graph that is sent off to process, and it's only when you do something, like in this case, count by keys or some other action, so that the Spark actually run the code and return the results to the driver. Now, most of the time, you don't want the driver to actually just get a data structure back. You probably want to write to disk or something like that, or do further processing. And so just another example of found a couple of different ways to implement this code. Where the first one, you can just see that I'm able to use this function that's been written by the Sparkling guys. So I can just pass Clojure functions to do this count count of event number by users. Or alternatively, I had to do a bit of Java interop for this aggregate by key. And here, because I'm now writing Java code and this takes Java functions, I just have to use the sparkling things to wrap my closure code and actually pass that down into the Spark JVM. And neither of these things actually trigger any actions by Spark. They're these sort of lazy things. So I just have to use collect, and I'm just asked. Collect is just sort of a bit of a thing here, just to give me back what the data structure processed. And now you can see that rather than going back a neat closure object, I've got some kind of Scala collection, but it does indeed contain the same result. And so if I was using processing this on a terabyte of data, then I'd have probably written that out to disk rather than tried to pull it back to memory. Okay, as I said, we've been using the core API, so we're working with RDDs directly, and so we're generally processing our data using closure functions on these map data structures. But one of the things we could be doing is migrating to the dataset API, which is a lot more declarative. It's either writing SQL directly, or you can just be sort of programmatically creating your SQL. And this dataset API is a lot more optimized than the RDD API. And so where we might be losing out in sort of speed and performance, because you've got to translate between this closure functions, these are going to be serialized and run in the JVM. The whole dataset API now becomes very much more programmatic, and they've done a lot of optimization, which means largely we don't have to write any closure code itself. It's just all about building out this graph, and it should be a lot more performant because it reduces a lot of the time. And so yeah, I just gave that same example where I parallelized my dataset as a file, asked the Spark dataset API to read it as a JSON file, and then I can just do group by user and count. And that, rather than in the previous case, I actually have to sort of be wondering which of combine by key and aggregate by key might be the fastest. There is also a group by, which is very likely the slowest. In this case, I can just rely on the engine to do the most optimal thing. Although one thing I did find when I wrote this example is, rather annoyingly, as I put my 7 in here as a corrupt user, sadly it decided that was just going to be automatically converted to a string. So just some things to watch out for when you jump APIs. Okay, yeah. So what was some of our experiences? I mean, we sort of had to learn Spark through Clojure and Clojure at the same time. Sorry, we had to learn Spark through Clojure, which was sort of meant largely taking the Java API examples and then translating them into the Sparkling API, using some of its docs, which were also very powerful. But one of the other things we also found is we're big AWS users, and so we were happily running Spark on our laptops, testing away, perhaps with just a gigabyte data set, maybe less, and then spun up an EMR cluster, which we've been using for MapReduce jobs, so we're very familiar with using this system, put our Spark job on there with a quite small amount of test data as things go, and suddenly found that things were crashing horribly. And so we had to come across this blog post here that I've linked in Tune Your Cluster, which just kind of gives you some explanation on how to optimize your Spark cluster. And if you are using EMR, this is very important. You're just doing things like telling the system how much memory is available to an executor, how many cores there are, how much parallelism you have. And it can actually be very useful as well when running in a REPL if you want to make it process a bit bigger data. And actually this setting is fairly small because it's what I was using in my own local session to produce the code and the results you've seen. Yeah, so what did we find? Spark is very scalable, as I said. We have been processing data over the same data sets with the same code base over a couple of orders of magnitude. Largely for the day-to-day, it does feel like it's a bit of an overkill of processing environment, though, because you have got a distributed processing environment. We're starting up clusters, they're spreading out RDDs, and for the most part, our batches we're trying to keep reasonable to keep the CPU time down. However, and course, we use it because we want that scalability for reprocessing, but some of our jobs we just skip that and go for something simpler. Sparkling does do a lot of the hard work when we want to write our Spark code, but Clojure isn't a supported language, and so we've got to make sure that library is being kept up to date. And in fact, it does seem to have fallen a little bit about the wayside. We've started having to extend it ourselves. But actually, the core part that you need with this sort of serialization is all there. I've generally found Spark's documentation pretty good. I particularly like just going through the Java APIs and trying to figure out what to do. But you do find yourself then sometimes, like just in this simple example I gave, where I suddenly do I group by key, do I combine by key, do I aggregate by key? And the documentation doesn't always give you the clear way of going. But a bit of Googling around will usually find a blog post or a Stack Overflow post to give you the answer. Yeah, when you're doing things, you're writing stuff in Clojure and you're sending that off to some system to process for you. If something goes wrong, you get a stack trace back, you're probably not going to get a line pointing to a line in your code. Or if you are, it's going to be some weird entry point you had, and it can make debugging a bit frustrating when you're just given a large amount of noise. Finally, yeah, dataset API is a lot more optimized than the RDD API that we've been using, so we can probably get some free performance gains from that. Although, as I say, this is even more declarative, and so even less likely to give us a pointer to where things go wrong. Okay, yeah, so that's largely my talk. I've just kind of gone through a little bit about Metail and the data we're collecting and what we want to do with it, and how we've gone about building our pipeline, what sort of paradigms and things are we using, and yeah, hopefully explain why we sort of using functional programming, why we chose Clojure, and also if anyone fancies having a go at sort of seeing some Spark and Clojure, I sort of tried to create a bit of a demo for this, but in the end found it too difficult. But I got quite a lot of Clojure code demonstrating the use of the Spark dataset API sitting online there if anyone wants to have a play. And if you're looking through my slides later, you can get a bunch of resources related to this. Thank you.
So we are waiting for any live questions right now? Okay, then let's go to Slido then.
Okay. How large are the Clojure projects in your company, and do you have many problems maintaining these projects? Probably the largest, I guess, must be in the tens of thousands of lines of code. The Mondo, the Metail experience I showed you, that's written in Clojure or Clojure script. I've never really looked at that code base, so I don't know how large it is. But there are a lot of views and a lot of different things going on there. We also use it a lot in sort of the setup where we're managing the garments that we're digitizing, and so that's kind of giving us this sort of server middle layer that's interacting with databases and REST endpoints. Again, I'm not entirely certain how large that code base is, but it is pretty large, and it's a fairly standard sort of RESTful web API to interact with a Postgres server. And I don't think there are any Clojure-specific problems with maintaining those. I think that is an area where the communities and there's a lot more activity going on, so there's a lot more support. Unlike our Spark code and the Clojure drivers that we've written are although fairly large, you're mostly constrained to one or two projects, and again, yeah, they're sort of fairly easy to maintain. Everything is batches. We don't have any real time. We've not implemented that. What influence? I think the main reason we chose Redshift was because at the time we had this batch pipeline and we were using the previous sort of version of our pipeline was using a tool called Cascalog, which was wrapping MapReduce, and that was really hard for our data scientists. It just had this exceptional learning curve. And so when Amazon released Redshift, AWS came out with Redshift, we were quite happy to give it a go and get on board. we're not that happy with it. I think it is incredibly powerful, but it's also incredibly frustrating as well. It's largely around the fact that whenever you go to some kind of talk about EMR, they explain how they've got this Hadoop cluster which has separated compute from storage because you're able to use S3 for infinite storage expansion, and then you scale your compute as you need. And then you go to Redshift and you're largely stuck with choosing between something with a large disk and low compute, or a small disk and large compute. Spectrum came along last year and kind of started to help alleviate these problems. But yeah, so we've kind of had teething issues with Redshift, and what's better? I'm trying to think of the answer to this. What was better choice in our experience? More smaller nodes or less but bigger nodes? I'm not sure how well we've got the data on this. Our pipeline is often bottlenecked by something that I didn't talk about, but we call out to DynamoDB during our batch pipelines to manage. It represents a user database basically, and so we can look up users. Actually, we found just the network traffic of using DynamoDB for that is largely our bottleneck, and so although it will scale to handle the throughput from the clusters, just the round trip time of going to the internet and back that's our current problem that we're trying to deal with, and so we haven't really properly explored the sort of smaller nodes versus larger nodes. Usually we just we've kind of optimized by looking at the cost and just seeing what processes it in the time that's acceptable. So we're probably more driven by the price of the node and just try and balance off that instead. Would I recommend Clojure instead of Scala for Spark? I've never tried to write Scala, so I can't really say that. Probably if you know neither, I suspect you're going to get better support, and you're going in it specifically to write Spark. I probably would say, well, try Scala, simply because you're using the primary language of the Spark ecosystem. But I I actually very much like writing in Clojure, but I think that it might be a pragmatic approach for a new user who's very Spark focused. Why didn't we opt for the data frame API instead of data set? I think just at the time we were getting into Spark, the sparkling support for the dataset API was much more minimal. We felt a bit more comfortable writing Clojure code rather than trying to understand this dataset API and extending the sparkling. So we were able to use those examples. Now I've had more time to sort of bed in with Spark and tried some other alternatives. I've got a much better feel for what's going on. And I was at a talk a couple of weeks ago that was explaining just how much effort has gone into optimizing the dataset API, and they've basically bypassed the entire Java memory model. So it does sound like it's very cool under the hood and would be a lot more performant. Would I consider a type-safe language out of the box like Scala instead of manually adding the type annotations in Clojure? I don't have a strong feeling on this. I think I'm personally quite interested in trying out Scala just because I've kind of tried out Spark and be interesting to get this type system and see how it behaves. My large interaction with types has been through C# and C++, whose type systems are not really the same, I don't think, as the slightly more mathematical type system that's in Scala. I've sort of just reading a bit about Haskell, so I'm sort of interested to try a language with a proper type system, as it were. So yes, I would consider it, but I don't have any good experience really to give a proper proper input into that sort of flame war, basically. I don't know what Scala cryptics are, so I can't answer that next question. I think the biggest data sets we're using, I'll take this to meaning our pure closure, they're probably only a gigabyte in size. And that's actually something where we're not really using an immutable data set because we've got a gigabyte of data and we can process that pretty quickly. So also because it's coming from a system that's also editing each own place, it's much easier just to grab the whole thing and process it. I think actually one of my colleagues for some one-off job has processed a data set up to 30 gigabytes just using AWS EC2 instance that had 32 gig of RAM or something like that, and was able to create a JVM large enough to allow him to fit the whole thing in memory. But someone else did that, so I don't know what the challenges were, but I do think it's possible.
So this is the we are run out
Okay.
of time. So thank you, Gareth, for your answers and presentation.
Okay. Thank you.